Hello everyone, welcome to our poster, The Interplay Between Seismicity and Hydrological and Industrial Process in Salt Lake Valley, Utah. Salt Lake Valley is located in the eastern margin of the Basin Range. The Salt Lake City segment along the central Wasatch Fault Zone has been due, so the recent magnitude 5.7 magna earthquake is not a surprise. Salt Lake Valley also contains the world's deepest open-pit mine and its annexed tailings impoundment. And the tailings deposition amounts to about 60 million tons per year. Interestingly, the magnitude 5.7 event is aftershocks and persistent microseismicity are next to this tailings structure. Another cluster in the east side seemed to fall in the east dipping West Valley Fault Zone. Together with the west dipping Wasatch Fault Zone close to the Wasatch Range, they constitute a graben that hosts a dynamic aquifer. While for the hypercentral zone, we believe there's a west dipping seismogenic structure from the Listric Wasatch Fault, while there are also suspicious east dipping structures, according to reading literatures, so we consider both geometry when computing the elastic stress changes due to various hydrological loading sources and the mass transport from the mine to the tailings impoundment, as well as the poroelastic stress due to the seasonal volume strain of the aquifer system. Those figures show the map view and site view of the column stress changes in the west dipping and east dipping scenarios. The first column shows that the long-term decrease of the Great Salt Lake from 1900 to 2020 by 2 meters unclimbed the fault. The second column shows that the aggregate tailings since 1905 can generate more than 100 kilopascal of column stress changes in the upper few kilometers and tens of kilopascal at the seismogenic zone, which is 2 orders of magnitude larger than the hydrological source. Depending on the exact location and fault geometry, the tailings can yield a stressing rate that may delay or hasten nearby ruptures. The third column shows the elastic stress changes due to seasonal water storage variation of a shallow aquifer, which is only in 0.5 kilopascal at the seismogenic depth. Ground deformation mapped by Sentinel-1 SAR imagery reveals an elongated aquifer, which is well bounded by the faults. It's featured with about 50 mm seasonal uplift and 30 mm horizontal extension and contraction, corresponding to 0.03 to 0.06 cubic kilometer water storage cycles. Phase shifts across the active faults in both water level and deformation suggest control by the lower permeability structures. We fit the inside displacement observation considering finite strain source in half space. We consider 2 end-member models with either the volume strain or the thickness of the cuboid to be fixed. The consequent distribution of the thickness and the strain are similar, suggesting consistent vertical integration of the strain source from these 2 models. We can also obtain the seasonal bulk volume changes. The seasonal stress changes on adjoining faults from poroelastic volume strain are 2 orders of magnitude larger than those from hydrological surface loading, but both are small at the seismogenic depth. Unlike the regular seasonal hydrological process and associated stress changes, historic seismic events do not show annual periodicity. We would like to thank our colleagues, data and software providers. For more information, please refer to our paper, preprint, and send us email. Thank you.